Welcome to Brain Vision.
The secret of this question is treating this part of the washcloth and this part of the washcloth separately, and only then join these two parts. By doing that, we are actually treating this system as another very familiar system which is much easier to deal with, which is this one. We have a block here, and this block has three forces acting on it, which would be WCA, normal force because it's lying flat on some kind of table. There is a frictional force that tries to hold it in place, and another force. So there are four forces, which will be the tension force. And here we have this object and a cable connecting this part to another part that is here. So on this other part there are two forces acting, this force and that force. So much easier now, isn't it? Much more familiar to us. So let us treat this problem, which is completely equivalent to the actual problem of the question. So what is the maximum fraction of the washcloth that can lie off the table before it falling down to the ground? So we are going to treat this system instead because it's much easier. So there are two axes of interest here, the y-axis and the x-axis, and we will be using both. Let me call this number 1 and this other number 2. By applying Newton's second law to number 1, we get the following. So for the vertical axis, we have that the net force on the y direction is equal to the mass mca times the acceleration on the y direction, which is equal to 0, because it's lying on the table, it's not moving, and it's not going to move. So the net force on the y direction is equal to 0, and then the net force on the y direction is composed by two forces, the normal force, which points to the positive vertical direction, minus the weight force that points to the negative vertical direction. This is equal to 0, so the normal force is equal to the weight force, as we can see from the beginning. Now, what happens when we apply it to the x-axis? So you're applying to the x-axis, we have the following. The net force on the x-axis is equal to the mass Ca times the acceleration on the x-axis, which is equal to 0 for the same reason the acceleration on the y-axis was equal to 0. Then the net force on the x direction is also equal to 0. But the net force on the x direction is composed by two forces, the frictional force, which points to the negative x direction, and the tension force, which points to the positive x direction. Then this tension force is equal to the frictional force. So far, what we got is the following. The normal is equal to the weight, and the tension is equal to the friction. Let me organize the board before applying Newton's second law to the block number 2. Okay, now applying Newton's second law to block number 2, we get the following. So note that in block number 2 there are only vertical forces acting. So we only have forces on the y direction, and then the net force in the y direction is equal to the mass, but now the mass of the table times the acceleration on the y direction for that second block. This is also equal to 0 because it's not moving. Therefore, the net force on the y direction is equal to 0 on the second block too. But on the second block, we have only two forces on the vertical direction. We have the tension force, which points to the positive vertical direction, and we have the weight force that points to the negative vertical direction. Therefore, the tension is equal to the weight force. Now let me organize the board and finish the question. We can finish this question by using these three equations that we had derived from the situation. So the second equation tells us that the tension force is equal to the frictional force. But note that this should be the static frictional force since nothing is moving. And the maximum value of the static frictional force is given by the static frictional coefficient times the normal force. But note that this equation was derived for block number 1. So the normal force here is this NCA. So times NCA. But now from the first equation, we see that NCA is equal to WCA. Therefore, the tension force is equal to the static frictional coefficient times the weight of the washcloth that is on the table. Now, from the third equation, we get that the tension, which is equal to this, so frictional coefficient times weight force acting on the washcloth that is on the table is equal to the weight force that acts on the part of the washcloth that is off the table. Then, remember that the weight is given by the mass times the acceleration of gravity. So, we have that WCA is equal to mCA times G, and W oft is equal to m oft times G. We can simplify G's here so that we get that the static frictional coefficient times mCA is equal to m oft. Then, the question asks us about the following. It tells us to calculate what is the maximum fraction m oft divided by mCA plus m oft. Using this relation, we can substitute the m ofts here by the left-hand side of this equation. So this is equal to mu s times mCA divided by mCA plus mu s times mCA. Now we can factor out mCA on the denominator to get mCA times 1 plus mu s divided by mu s times mCA. So these factors of mCA are simplified and we get mu s divided by 1 plus mu s. Finally, using the value for the static frictional coefficient, we get 0.4 divided by 1.4, which is approximately 0.29. So this is the maximum fraction of the washcloth that can rise off the table without bringing the whole washcloth to the ground.